Hey guys, welcome to video 26. Today we're going to continue talking about first order RC filters, and we're going to look at decibel response, Bode plots, and if you stick around to the end we're going to do a little PSpice too. So starting with some review, on the left hand side we've got the schematics for the first order RC low pass and high pass filters. In the center we've got the response equations that we derived in the last video. Now the first version gives a response in terms of R and X sub C. The second version, which I prefer, gives a response in terms of the input frequency and the critical or corner frequency. Now on the right hand side we have graphs of the response versus frequency, and remember at the corner frequency the response is down to 0.707 times the maximum value. If we wanted to give the response in decibels, we would take the log of V out over V in and multiply it by 20, and I have that summarized here on the next page. For amplifiers, we usually represent the gain with the letter A. For filters, we represent the response or gain with the letter H. Now, this table on the right-hand side shows the decibel values that correspond to a number of interesting response ratios. So if V out over V in is 1, that corresponds to a 0 dB response. If V out over V in is 0.707, which occurs at the corner frequency, that corresponds to a response of minus 3 dB. The reciprocal 0.707 is 1.414, the square root of 2. That corresponds to a 3 dB increase in response. Now let's look at tenfold changes in response. So let's say we go from a V out over V in of 1 to 10. That takes us from 0 dB to 20 dB. And similarly, if we go from 10 to 100, we go from 20 to 40 dB. And from 100 to 1,000, we go from 40 to 60. So notice that every time we increase our response by a factor of 10, we increase by 20 dB. Similarly, when we decrease our response by a factor of 10, if we go from 1 to 0.1, we go from 0 dB to minus 20. From 0.1 to 0.01, we drop 20 more dB, and so on. All right, now, when we have a graph of response in decibels versus the log of frequency, that's called a Bode plot. All right, so a Bode plot is a log-log amplitude response plot. Now there's also a phase plot versus the log of frequency, but we're not worried about phase response today, so don't worry about that. Let's just deal with amplitude response now. All right. The amplitude response, usually in decibels versus log of frequency, is a Bode plot, and that's attributed to Hendrik Bode, shown over here. And if we look at a first order low pass filter response down here, what we see is that the frequency axis is expressed in factors of 10 above and below F sub C, and the response axis is expressed in decibels. Now our actual filter response is this black curve here, and notice that as we move to the left of F sub C, that curve gets flatter and flatter and flatter. All right, and as we move to the right of F sub C, that curve approaches a constant slope. All right, that constant slope or horizontal response is called the asymptotic response of the filter. That is, it's the response the filter approaches in the limit as frequency approaches 0 or infinity from each side of the critical frequency. All right, the Bode plot could be given in terms of the actual response or the asymptotic response. Usually it's easier just to, think about the asymptotic response. All right, now remember, a decade is a tenfold increase or decrease. So we're going in decades here from FC to 10 to 100 and so on. An octave is a doubling or halving. Okay, now Let's look at the asymptotic responses for some different orders of filter. We've only been talking about first order so far, and when we look at the asymptotic response for a first order filter, here it is, and we see that the roll-off rate of the filter, that is the slope of this response curve, is minus 20 dB per decade. So every decade we go out in frequency, this response drops by 20 dB. A second order filter would drop off at a rate of minus 40 dB per decade. And a third order is minus 60 and so on. So every time we increase the order of a filter by 1, the roll-off rate increases by 20 dB. All right. Now, just so happens that a 20 dB per decade change is the same thing as a 6 dB per octave change as well. But normally we're going to be working with decades. All right, so before we move on, just notice that every time we increase the order of the filter, it gets closer and closer and closer to the ideal brick wall response. We can never reach it, but if we keep increasing the order, we can get closer and closer to it. All right, now why do we like to use log graphs to express frequency response? Well, let's take a look here at graphs of the response equation for a first order low pass linearly versus the response in decibels. Okay, notice that most everything that happens with the filter is compressed into a very small span when we have a linear frequency axis and a linear response axis. Now if we go to a Bode plot, which is log frequency, log response, note that we get the nice asymptotic responses as we go out from the center frequency, and this is generally easier to extract information about the filter from just by glancing at it. Much easier than looking at this one. So that's why we like to use Bode plots or log response plots. All right, now I'm going to do a little bit of PSpice simulation here. It's a great circuit analysis simulator. I've used it for decades. And there are other ones out there. There's LT-Spice and others, but I still prefer to use plain old-fashioned PSpice. So let's simulate this circuit. All right, I've created a circuit here that's got a critical frequency of just about 1 kilohertz right on the button, and I'm going to simulate this using PSpice. So let me bring up PSpice. This is my schematic editor, and what I'm going to do now is draw this schematic. All right, I'm going to walk through this pretty quickly, but we'll cover this in more detail in later videos. But for right now, let's just blow through this. All right, so we're going to draw, and I'm going to get a new part, and let's start with the resistor here. So I'll just type R for part name, and it's the first one that comes up, so I'm going to place that. All right, then I right-click to drop it, and now I'm going to look for a capacitor, C. And there it is, first one on the list. I'll place a capacitor out here. And the next thing I want to place is a sinusoidal voltage source. All right, so that's beginning with the letter V, so I've got VAC. I could use that, but I'm going to use V sine. So let's see, VS, there it is, V sine. We'll place that and right click. And we'll close this window for right now. I'll open it again if I need to. So here's my sinusoidal source. I'm going to move it up here. I'm going to bring my resistor up here. And the capacitor, I'm going to rotate 90 degrees by hitting Control R. And then I'll drag it to its position. All right, now I'm going to move these labels to nicer positions, and I'm going to double click V1 and change that to V in, because I like to call my input source V in. R1 is just fine, and it's not going to be 1K, so I'll drag that value up here, double click it, and change it to 1592 ohms. All right, then the capacitor C1, I'm going to change its value by double clicking on it to 0.1 UF. Now the U stands for micro. PSpice knows that means micro. It ignores the F. I just put that there for my own reference. All right, so now our capacitor is 0.1 microfarads. And notice PSpice leaves all these artifacts on the screen. I don't know why it does that. It's done that ever since we went from Windows XP up. So if I want to clear all this stuff, I just click on this little redraw symbol and it clears that stuff off. Next thing I want to do is wire these parts up. So I'm going to come up here to this pencil that says draw wire, click it, and click. I've connected these two. Now I'm going to connect these two. And now what I need to do is put a ground down here. So let's draw, get new part, and I'm going to use an AGND, and there it is, analog ground. We will place that here and here, and there's our schematic. Okay, you can move things around to make it look nice. Okay, if I wanted to, I could drag this out further. I'd have to fix those jagged lines, but there you go. And every time you highlight a component by left clicking, it turns red. Then you can edit that. All right, let me refresh the screen. All right, now what we have to do is set up this input voltage source. So I double click the sine wave, and here come the parameters for this sine wave function generator. All right, DC value, double click it. I don't want a DC value, so I'll set that to 0. AC value, we're going to use that for frequency sweeps, and I'm going to set that to 1 for convenience. We have no offset voltage, so I set that to 0. The amplitude, let's make the amplitude of this thing just 1 volt. And frequency, since our corner frequency is 1 kilohertz, we'll make that 1 kHz. Okay, PSpice understands that K means kilo. All right, so we'll enter that, and then we'll just hit OK. So now we've set up our source for 1 kilohertz at 1 volt peak. All right, now we have to set up the analysis to tell PSpice what we want to do. So we come up here to analysis and then set up. All right, we're going to do a frequency sweep. So we're going to do an AC sweep. That is, we're going to sweep the frequency of this sine wave in decades from 10 hertz to, let's go to 100 kilohertz, 100 kHz. All right, so we're sweeping it from 10 hertz to 100 kilohertz in decades. 101 points per decade is the default. That's pretty good. We don't worry about the rest of this. We'll just hit OK. We'll close this. And now we come up to analysis, simulate, and PSpice wants us to name this schematic before it saves it and analyzes it. So I'm just going to call this first order LP. So that's our first order low pass. Okay, we'll save it. And now PSpice is crunching through the analysis, and in the back here it's brought up basically an oscilloscope, or in this case a spectrum analyzer for us. So notice the horizontal axis ranges from 10 hertz to 100 kilohertz, and it goes in decade increments. The vertical axis, well, that hasn't been set yet. We have to tell it what to do. So here's what we're doing next. We're going to add a trace, which is a scope trace, and it lists all of my circuit parameters that I can plot here. What I'm interested in is the voltage drop across the capacitor. So I know, because I rotated the cap, that its second node is vertical. So we're going to look at the voltage across C1 as a function of frequency. And there it is. All right, now this is not in decibels. All right, so we're going to now change this to the voltage in terms of decibels. Okay, and to do that, all I do is type dB in between V and the parentheses, and here's our response in decibels: 0 dB, minus 10, 20, 30, minus 50. So we can see that the response of this circuit drops to about minus 40 dB at 100 kilohertz. That makes sense, right? The critical frequency is 1K. This is 2 decades, so it should be 40 dB down, and it is. Now let's see where the corner frequency is by activating a cursor, and I'm going to drag it out here to 1 kilohertz, and we see at 1 kilohertz we're down by 3.01 dB. That's actually what it is. All right, so this is, you know, simulating the stuff that we've just been talking about. Okay, so I can move the cursor anywhere I want, but right here at the corner frequency we see the response is down by 3 dB. All right, that's a quick look at how we could use PSpice to analyze a circuit like this. Now there's a lot more that we could go into. It's an extremely powerful program, but if you want to see some more, stick around for future videos. We're going to delve into this a lot more deeply. But for today, that's all I've got for you. So I will see you in the next video.